Looks like we're just about there. Welcome back, folks, so far. And it's official. Looks like we're about to finish off our week number 4, going into week 5. Hopefully we get some more people to log in, but at the moment, any questions at all to start us out? Okay. Well, the big announcement, of course, is that next Tuesday we'll be having our very first exam. And for a class like this one, where it's just completely fully online, it means we won't have an actual official class next Tuesday. Presumably, someone could schedule their exam in a testing center right at 6 o'clock. And so holding a class just wouldn't make sense. Plus, doing an exam on Tuesday and then doing a 75-minute class on Tuesday seems like just too much for one single day. So on the days where we have exams, we won't hold an official class, but we'll be back to our usual class on Thursday of next week. So everyone should have instructions on how to schedule your exam, and you should schedule that exam as soon as possible. Some people are testing in the Idaho Falls Testing Center, some in the Pocatello Testing Center, and you should have a link that was sent to you through the Canvas messaging system with instructions on how to register. Any questions on registering for the exam, scheduling it?
I have a question. It's not about scheduling. I've got mine scheduled, but is it going to be a paper exam or is it going to be on a computer?
It's going to be a paper exam.
Okay.
So pretty traditional kind of exam. It's going to be printed out. It's going to have your exam material on both sides. Kind of imagine it looks like this one right here, sample exam 1. The only difference is there's plenty of white space between the problems for you to write down the answer.
Okay. Thank you.
Yep, absolutely. So whichever testing center you're in, it's going to be a paper exam. Again, imagine this one, but actual lots of white space to fill in your answer, show the work. At the end of your exam, you might finish it early. You'll just hand your exam to the proctoring center, testing center staff that's helping you out. And what they do is then they just scan the exam and they email it directly to me. When I get your exam, I'll be marking up your exam, something like this. If these are correct answers, I know they're just questions. That'll give you a score out of the total points possible. So kind of like how I'm grading your quizzes. In fact, the quizzes were meant to show you kind of a format of what real exam questions might look like. Quiz number 2 is due today, and quiz number 3 is going to be the next quiz. Just take a look at them, just for the sake of taking a look at them. So the exam questions are going to look about like this with white space. The way I've been grading your quiz questions are going to give you an idea of how the exam questions are graded. Unfortunately, the exam is closed notes. Exam 1, 2, and 3 are closed notes, but on the third exam, there will be a formula sheet that's attached. So it is a closed notes exam. And let's see, what was that other thought? Oh, and as far as quiz 2 goes, I'm going to try to get the quiz 2 graded as soon as possible, probably starting grading them tomorrow on Friday. I'll give you your feedback on how this one went, and this will give you a good idea of how prepared you are for a question that looks like this one. Quiz number 3 is another great quiz. This one could be very similar to a problem that's actually on the exam itself. So if you decided to solve this one early, email it to me on Friday, Saturday, Sunday, or even Monday. Its due date is still the 25th of September, so a week away from today. But if you send this to me early, I'm going to make every attempt to grade this early, send it back to you so you'll have a good idea of how you're doing on this question to help you out with the exam. Oh. Other questions at the moment?
When are you gonna send the link so we can sign up for the exam?
I should have sent you a link already, but let me put down a quick reminder. I'll resend that link tomorrow morning so that it should show up again. But yeah, I should have sent it already. Sorry that you haven't seen it yet. What I did was I sent it through the Canvas system. So it'll be somewhere under this spot right here where you would get your inbox messages out of Canvas. But let me make a new reminder here. Resend exam schedule link. So I'll get that sent out first thing tomorrow morning, probably even around about 7 a.m. That's going to come through. Sorry you haven't seen it just yet. And one thing that I'm not too sure about, because I'm new to Canvas as well, when I send a message through this little inbox system, you should see a message there. And I think you should also see a message in your ISU email, just like the duplicated message. Does that sound about right to folks with how Canvas works?
Yes, I
Yes.
think that is correct.
Also, that's good to know. Thanks for letting me know. So yeah, I'll try to get that sent out again. It doesn't hurt to have a second reminder as well. So thanks for asking about that, Clay. Other questions at the moment? Okay, so if you complete that quiz 3 early, say before Tuesday, I should be able to get this graded and sent back to you just to give you extra practice. If you want more practice, this is a list of very similar problems to what you're going to see on the real exam. Solutions are at the very back of this document right here. So this is a great one to practice, pull out some paper, maybe even put out a 75-minute timer, try to solve all of them, and you'll get a good idea of how prepared you are for this upcoming exam. And if you want more practice, I think we've shown this before, go to the Newton Alta homework system, and there's a sample exam built inside there for exam 1 as well. It's purely optional. It doesn't affect your grade whatsoever, but it's just another resource full of practice problems. Well, our schedule's tight in this semester. The math department makes me go through specific sections so that we stay caught up with the course on the final exam. So we have to go through section 4.1, 4.2 today, but the exam is only going to go up to section 3.3. But any other questions, folks, before we get started back in section 4.1? Okay, well, let's jump back in where we left off. This is material that's going to be on our upcoming second exam, so not in the first exam. And what we were doing in this section was solving what we refer to as systems of equations. That means two equations, like this first equation here, the second equation here. We're looking for a pair of values, x and y, that's going to make both equations true simultaneously. On this method, using the elimination method, pretty much all we did was we took both of the equations, we added them up. So we went across the columns, added the like term pairs, x canceled, 3y plus 7y equals 10y. We added up the right-hand side, and we've got another equation for which we can solve for a variable immediately. So our first step in the elimination method was just add up the equations. Once we got a value for y, we took this equation, recopied it, and just substituted in the y value, y equals 1, so we wrote it in that spot. They gave us another equation from which we can solve x on, and we said the solution is 6, 1. We're writing the answer as an ordered pair x, y, and this is just a reminder that x is 6, y is 1. So we'll practice one more of these kind of problems before going on to the next section, 4.2, to see how those go. But any questions, folks, on getting through this one? Okay,
How did you
so
determine what y was?
it came from when we added these two equations here. The x values simplified down to this right here. So we got y equals 1 because all we had to do at this stage is just divide both sides by 10, and then it gave us this y equals 1. So the step in the middle would have looked like this. Tens would cancel, and this would have left a 1 there. Does that make sense with that question there, Clay?
Yeah.
Awesome. Other questions at the moment? Okay. One of the things you might notice about math is when you come back to a problem like this, it's actually really hard to look at because all of the steps are here all at once. That's a lot of visual information. Sometimes the best way to get a feel for how to get through this problem is just do it all over again or do a separate problem. So here's a new problem where we're going to see the method go from start to finish from scratch. But notice this one's not as nice. This one's a lot more challenging, so this is good practice. The trouble is we can't just add up the equations and get something helpful, because if we add this column, 9x plus 5x is 14x, add this column, 2y minus 6y is negative 4y, and neither variable eliminated. We're supposed to be using the so-called elimination method, but nothing eliminates when we go to tally the equations. So this is one of the problems where we need to take an extra step to really even get started on this one. Oh, and it's also a reminder that on the upcoming exam, it is closed notes, but it is open calculator. So don't forget to bring a basic scientific calculator. Sometimes the numbers get a little bit larger, and that's going to happen on this one. So I forgot to load the calculator again. Let me get this going. Okay, I think I'm actually prepared now to get through this problem. So first thing I'm going to do is just copy down the equation, 9x, both equations, plus 2y equals negative 42, 5x minus 6y equals negative 2. And now, even though if we add up both of these equations together, we're not going to eliminate a variable, we can still force a variable to be eliminated some way, somehow. Looking at the column for x, the 9 and the 5, well, it's not convenient to make this work because the least common multiple between 9 and 5 is 45. I can multiply this equation by negative 9 and get negative 45. Multiply this equation by 5 and get positive 45, but that would be working really hard. Another thing we might try is, notice how close these are. If we were to just have a 6y right here, this would be a really fast problem to solve. But we can make that happen. We can take this entire equation 1 and multiply by, all right, mult dot for multiply, by 3. Let's do just that. We'll get 27x plus, let me fix my penmanship first, plus 6y equals, this is the point at which I need a calculator, just not ready to go with 3 times negative 42 at 6 o'clock in the night. So that comes out as negative 126. For the second equation, let's just copy it. We copy that equation down. We now have 5x minus 6y equals negative 2. And look what we've manufactured here. Just by tripling both sides of the first equation, we have positive 6y, negative 6y. This problem now essentially starts out just like the last one. Let's peek at the last one for just a moment. The last one was nice because it was just ready to go. We had positive x and negative x, add up both equations, and the variable x eliminates. That's the elimination method in action. This time, we're eliminating the variable y because we have 6x, or 6y rather, and a negative 6y in this column. So this is the step where we would add everything up. In this column, 27x plus 5x gives us 32x. And we get a 0 from here, 6y minus 6y is 0. So we just take negative 126 minus 2 for a negative 128. And we're just about there at this point. Divide both sides by 32. X now equals, let's take a look into the calculator. I mean, that one shouldn't be too hard. That should be negative 4, but let's be extra sure. Negative 128 divide by 32, comes out as a -4. So x is -4, and we're halfway done. Our goal is to write down the solution as an ordered pair, an x coordinate and a y coordinate. So the x variable would be -4 here. The moment we get the y variable, the y coordinate over here, our work is done. Any questions to this step, getting up to that -4? Okay, next thing we do is we go back to the original equations. They're the ones that are in the most simplest form, and pick either one you want. Equation 1 looks more complicated. The numbers are larger for all these coefficients. So I'll go for the second equation. Amazing fact about this is you can pick either equation and get the right answer. But if we pick the least amount of work, we're going to be the most accurate. So I'll go 5x. Let me make sure I have enough space to write that in. Recopy that equation 5x minus 6y equals -2. We just said on paper, x is -4. So everywhere on this entire problem, you can plug in a -4 and get a true statement, including right there. And the moment you do that, you get this equation. 5 times -4 for that variable x minus 6y equals -2. And this is an equation from which we can solve for the y variable and end the problem. So let's run through the normal algebra for this situation. Here we have -20 minus 6y equals -2. Add 20 to both sides, and -6y is going to be equal to +18. And I'm running out of space, so I don't want to cram that together. Let me recopy it here. -6y equals +18. Divide by -6. And y now equals -3. So we just plug that -3 back inside here. And this is the solution to that set of equations. Well, we did it, folks. This is our rundown on how to solve system of linear equations. This takes a lot of extra practice, a lot of finesse, sometimes a little bit of creativity, like multiplying by 3 alerted us. This could eliminate the y variable. So we do need more practice getting through these. And the good news is that's what section 4.2 is all about coming up next. The only additional thing we're doing is we're setting up a word problem at the same time, so we'll have to navigate through that. But every one of our word problems is just going to turn into one of these, a system of equations like this. Any questions at all, folks, before we take a look at the next section? Okay, let's take a look at how those go. So we're in the section 4.2, applications with systems of equations. We mentioned before, applications is kind of a math buzzword to say, essentially they're word problems. So these notes are pretty bare bones. It's just one example per page, one problem that we're going to solve. This is a good set of problems to come back to when you're doing the homework set in the Newton homework system. I've tried to match up the kind of problems we're solving here pretty closely to the kinds of problems that are going to show up. So you can use this as a guide to help out with those. So let's read through this, see what's going on. We're told a textbook store sold a combined total of 284 physics and biology textbooks in a week. So that's interesting information. Sounds like a generic word problem. The number of biology textbooks sold was 46 less than the number of physics textbooks sold. So we somehow know that information. We know the total and how they relate to each other by this highlighted statement. The question is, how many textbooks of each type were sold? Well, that's an interesting question. There's physics books and biology books. So one way to start this off is let's assign some variables. You can let this be X and Y if you like. But sometimes when you're doing an application, it's a good idea to label your variables as closely to the actual thing you're looking at as possible. We'll do some X's and Y's, but just for the sake of that last comment, let's let P stand for the physics textbook. We know 284 sold. We want to know how many of each type are sold. So P is going to be equal to the number of textbooks. Let me say more specifically, the number of physics books sold. Let me try to spell that better. There we go. So essentially what we're doing here is we're writing out a step-by-step procedure that's going to take all of this, a confusing real-world situation, kind of a weird real-world situation, and try to extract away from it so that all we have is a system of equations, because that's the thing we're much better at solving. So think of this as step one. Step one, we're defining what the variables actually mean, so we can use the information provided. The other one is a number of biology textbooks, so we can write B equals the number of biology books sold. So step one is just assign variables like we just did to the things we want to solve for, the unknown quantities, in other words. And now because there's two variables, oftentimes we're going to need two equations as well. Here's one equation we could start with. We're told the textbooks sold a combined total of 284 physics and biology textbooks in a week. Well, that means if P is the number of physics books, B is the number of biology books, you can just straight out write P plus B equals 284 books. Because the left-hand side is the total number of books sold, and we were told the total number of books sold is equal to 284. So that's equation one down. We need another equation if we're going to solve this. That's where this sentence comes into play. Let's maybe break this up a little bit, just to see how this relates to what we've done so far. So reformatting, just for the sake of making the notes a little bit more easy to read. It said the number of biology textbooks sold, well, that's just B. Was is like saying is. It just means a literal equality. 46 less than, we can write that as a minus 46. We're reducing something by 46. The number of physics textbooks sold, but that's just, oh, let me fix my color coding. The number of biology textbooks is in green. I think we've made this comment once before. Color coding only works if you stay consistent with it. Sorry for that distraction there. Green for the biology textbooks, and blue for the physics textbooks. That's our second equation we needed. If we read it out, it just says, see the key for what B and P represent. Number of biology textbooks sold was 46 less than number of physics textbooks sold. So this is the same exact statement as what's up here. Let's carry that down. B equals P minus 46. And this is our step two in the entire process. Write down a system of equations involving the unknowns that came from step one. So we have two equations. Notice that one of the equations already set as a variable that's been solved for. So this takes us to step three. Solve. And the way we'll solve this is, let's use elimination method. or excuse me, the substitution method. Use substitution. Substitution works really well on this one because B is already solved for. We can take this and just plug it in directly right there and now solve for P, the number of physics books sold. Before we make that substitution, oftentimes this is the hardest part, step 1 and step 2, writing down the unknowns and then writing down the two equations. Any questions at the moment on either one of those steps? Okay, well, let's make our substitution next. We have P plus, I'll put a parenthesis where B was, just to show the substitution. Inside B, we're putting in P minus 46 equals 248. So once we made that substitution, these parentheses can just be dropped right out, straight out, and you just have P plus P. So 2P minus 46 is 248. And we're on our way. Let's add 46 to both sides.
Excuse me, you got the numbers mixed up. It's 284.
Oh, thanks a lot for spotting that. My dyslexia is showing up a little bit on this one. That's one of those awful mistakes where if this was a problem on Newton Alta, we could have lost all the credit on it. But that's a kind of a good mistake to make just for a sake on grading exams. If this mistake happens to you on an exam, and this is a 5-point question, you might lose just 1 point right here. If all of the rest of your algebra is correct, but maybe you just miscopied like that, thanks for spotting it, then you're not going to get dinged on every single part there. Maybe just minus 1 point. But let's do this accurately. Let's go 284. And now add 46 to both sides here. So we'll have 284 plus 46. We're now up to 330 altogether. So 2P equals 330. Then let's take that 330, divide by 2. We'll be dividing by 2 on both sides of this equation. And we have P equals 165 books. So 165 textbooks were sold. We're not done quite yet. We needed to find how many textbooks of each type were sold. This is just half the information. We don't have to write it as an ordered pair for these kinds of problems. So if you just leave it as P equals 165, then that's good enough for me. We need to get the number of biology textbooks sold, but that means we just go right over here to this equation, rewrite it, except now we can make this substitution. The 165 books goes here for P, then minus 46. So take 165 minus 46, and B equals 119. Let me check my arithmetic on that. One of the things I find with math is arithmetic is always the first thing that goes when you get tired. So even if this was an exam question, I'd probably just double check some of these larger computations, even if I felt really good at doing mental arithmetic like that. Somehow I got it right. I didn't feel too confident about it. B equals 119 books. So it's kind of a silly math problem in all honesty. Who would know, even if you worked for the textbook store, how would you know that 284 books were sold in a week, and then somehow know the number of biology textbooks sold was 46 less than the number of physics textbooks sold, and then somehow you don't know how many textbooks of each type were sold? That doesn't really seem like a realistic real-world situation. So think of example 1 as really just a kind of a silly math problem, getting us started to get into more serious ones down the line. Lots of more pretty interesting ones at the end of the notes here and in section 4.3. And this is kind of like a warm-up problem to get us started. Some people like to end the problem by just writing out So there was 165 textbooks sold and 119. Let me start again. Some people like to end their problem by writing. So there was 165 physics textbooks sold, and there was 119 biology textbooks sold. And that's not a bad step to take at the very end. But if you have P equals 165, and you already wrote on paper, P is the number of physics textbooks sold, you don't really have to restate that. It would be actually redundant at that point. If you don't say what B and P are, then you do have to clarify that at the very end, that goes to the physics books, 165, and 119 goes to the biology books, 119, and that would be a good clarification. Well, that's our first one down. Any questions before we try the next? Okay, so let's take a look at this new weird scenario we're in. Something about a person named Drew. Drew burned 1,800 calories Friday, playing 1 hour of basketball and canoeing for 2 hours. That's a really sweaty session, it sounds like. Then Drew's an active guy, it says next. Saturday, he spent 2 hours playing basketball and 3 hours canoeing and burned 3,200 calories. So that seems like a lot of work, that this guy has a lot of free time somehow. I guess that was the weekend. And the question is, how many calories did he burn per hour playing basketball? How many calories did he burn per hour while canoeing? Feels like a different kind of question, but you know what? It's really kind of the same. This one might be a little bit more realistic in a certain sense. Maybe Drew has a fitness app and he's tracking these things and just might want to know, how intense is playing basketball? How intense is canoeing? This could be something that could happen to you, for example. Well, the big questions are right here. How many calories did he burn for playing basketball? So let's make that be one variable. B equals calories burned per hour playing basketball. And the other one is, how many calories did he burn per hour when canoeing? So let's call C for canoeing, seems to make sense. C equals calories burned per hour canoeing. Hopefully not in the wrong spot in the Snake River. That sounds pretty treacherous. Now we have to relate all this information we have here to the other statements that was made in the rest of the problem. For example, it said 1,800 calories Friday, playing 1 hour basketball and canoeing for 2 hours. Let's separate this one out as well. Oh, darn, separating that out causes some problems. We'll fix that in just a minute. Let's put a little page break here as well. I guess that's not grammatical. That's going to bug me staring at. There, that's happy with a comma. Let's let that slide. So canoeing goes here. Playing basketball is that color. Let's start at the very first sentence. 1,800 calories, playing 1 hour basketball and canoeing for 2 hours. Well, these are calories burned per hour. So if we multiply by hours into B or C, we would just get the total calories. So this could be rewritten as 1,800 equals 1 hour of basketball would be 1 times B plus, from the and, we're totaling things, canoeing for 2 hours. Well, variable C is calories burned per hour. So if you want to know how many calories if you went for 2 hours, take the 2 hours times C, calories per hour, and that's one equation down. We'll recopy it down below here, but this is the process for getting the equation out of this first sentence. The hours that there's provided is just telling us what to multiply the variable by to get total calories on the left. Then second equation in a different format, but let's just keep that format the same. He spent 2 hours playing basketball. So that's 2 times B. And is just going to give us a plus like before. 3 hours canoeing. So 3 times calories burned per hour canoeing, multiply it by 3 hours, and we get the total calories from canoeing. Same here, this is the total calories from playing basketball. And this total equals the 3,200 calories. So that's equation 2 at that stage. So if saying variables was step 1, thinking in terms of variables B and C, step 2 is essentially done. We have all the equations we need. Let me copy them down below. 1B, or let's just simplify that. B plus 2C equals 1,800, coming from the equation 1 here. Then 2B plus 3C equals 3,200. So we've got 2 equations, and this set of equations can be solved either way, either the elimination method or the substitution method like we did on example 1. It's completely up to you. Either way, this is step 2. Now we just need to pick a method for solving this, and that'll be our step 3 next. So, even though if we add up the equations, we don't get what we want, it's not a bad idea to multiply equation 1 by -2, because then we can eliminate the variable B. And that's not too much of an extra work. The elimination method will work pretty well on this one. So let's go for elimination method just for the sake of practicing it as well. And also, I think it's a pretty good call on this one. If you really like the substitution method, I should emphasize no harm done. Even the Newton homework system, if they say you have to use the elimination method, no one's going to know if you use the substitution method. But sometimes one method is easier than the other, so the best strategy here is be familiar how to use both so that you can take advantage of just the more direct approaches when they come up. So to make elimination work on this one, I'm going to take equation 1, multiply by, I want to eliminate B, so I want a -2 right where that B is by the red dot. So let's just straight out multiply by -2. That will make that happen. The equation is now -2B minus 4C equals -2 times 18 is -3,600. We'll copy down equation 2. So 2B plus 3C equals 3,200. And now just tally those equations. By the way, we should call this step 3. We're using elimination method. So the variable B eliminates, like in the namesake, elimination method. -4C plus 3C gives us -C. And -3,600 add 3,200 gives us -400. All we have to do is multiply both sides of this equation by -1, and we're halfway done. C is now equal to 400, and that's half the problem. Turns out Drew burns 400 calories per hour canoeing. I have no concept if that's a lot or a little. I've never been canoeing, but that's what Drew would discover if his information above here is all accurate. We need to find calories burned per hour playing basketball. I don't know if that would be more or less, but we can solve that pretty quickly from here. Before we go to solve it, any questions getting the value C? Okay, the next thing you want to do is take 400, plug it either into this equation or the equation below. I think the first equation is easier again. The numbers are more contained. So let's plug it in there. First, I'll recopy it. B plus 2C equals 1800. Then another substitution. We've done loads of substitutions already. It seems like a lot of math is just doing this. B plus 2 times C is 400 that we just solved for, so we just drop it in there. Equals 1800. Then multiply 2 by 400. B plus 800 is 1,800. And lastly, B equals 1,000. Subtracting 800 from both sides. This would be in calories per hour playing basketball, and the C over here would be calories per hour canoeing. I guess canoeing is more passive. It kind of makes sense in a way. Well, we did it, folks. This is a strange set of information, but again, it's kind of realistic. You might have a fitness app tracker that could actually tell you how many calories you burned based on your heart rate. You might be timing your activities. And if you just wanted to solve for these things, the individual activities, canoeing versus playing basketball, you now have the tools. You can make this happen. It's still kind of a silly math question, but they're becoming slightly more realistic, hopefully, as we go. Any questions at all getting through this one? Okay, I do have a pretty good amount of problems in here because I feel like application problems, application sections like these tend to be kind of tricky. So really the best way to get good at doing these is to do a lot of them. So we'll do a good amount of them on these notes. We'll do all the way through the final example, the fifth one down here. So next one is a uniform motion type of problem. That means it's starting to get even more kind of realistic as terms of how valuable these kind of problems are. It's kind of a physics problem now in this sense. The uniform motion formula says if an object travels at an average rate of speed r, so r is rate of speed, for an amount of time t, usually in hours or it could be minutes, then the distance traveled, d for distance, is the distance equals the rate times the time. Not a bad idea to pause right there and just imagine just a rough scenario to get this in our minds. So if we say, for an example, I drove to a city going 75 miles per hour for 2 hours. Then we could use the uniform motion to determine the distance that I'm expected to have traveled. The thing that's implied here is that that's an average, that I've gone an average of 75 miles per hour during my entire 2-hour trip. Sometimes that part kind of gets glossed over, but that's one important fact about using this formula. We can say distance is going to be the rate of speed that I went, 75 miles per hour. And we could write it this way, 75 miles per hour multiplied by the time was 2 hours, let me write the unit in the same way just to make it not look weird, 2 hours. The hours down here in miles per hour cancels off with the hours here in the 2 hours. Now it's just 75 times 2 with the same unit, 150 miles. So that's the crash course on the distance equals rate times time formula. It's a tricky formula because there's really 3 variables we have to account for all the time. There's 3 variables we have to account for when we use this, rather. We have to keep in mind what the rate of speed is going to be in the problem. So that's going to be r. We have to keep in mind the amount of time that's going to be in the problem, and that's going to be t. So with those 2 in play, d just tells you distance traveled over that time period. One important comment, though, is sure, that's one formula, but often when you use this in application type problem, the formula is used twice. So sometimes that's something that is a little bit confusing about this. We don't use it just once. We're often tracking two objects or two people, two things moving at the same time. And so we're using this formula for each individual in the problem. And here's a typical kind of problem along these lines. It's really short, but it's actually jam-packed with information. It starts off by saying two cyclists start at the same point, travel opposite directions. So that's all we know at the moment. While we're reading the problem, it's not a bad idea to actually just put down a diagram. So here's one cyclist going this way, another cyclist going this way. One cyclist travels 3 kilometers per hour faster than the other. I guess this is maybe in Europe, we're doing kilometers per hour, or lots of places don't use miles per hour, actually. We don't know where that would be. Well, one goes a little bit faster than the other, and this is the common point that they started on, that dot right there. I'll call this arrow the faster cyclist. This one is going to refer to the slower cyclist. And, well, we have information about their rates of speed. Let's come back to that statement there. We're also told the cyclists are 207 kilometers apart after 3 hours. So this is a diagram where one ends at one point, the other cyclist ends at the other point on this arrow diagram, and the distance from here to here is 207 kilometers. So in other words, the total distance. Next thing we could say is they gave us some really key information. They were 207 kilometers apart after 3 hours. So this whole diagram will only make sense in one instant of time, and that's when t equals 3 hours. Well, we're getting started on this. We probably need something additional before we get too far. We never really use the information here. One cyclist travels 3 kilometers per faster than the other. And we haven't read the question yet. The end question here is, what is the rate, or in other words, rate of speed of each cyclist? So there's 2 cyclists to take into account. We want the rate of speed for both. And this is a good time to now enter in some variables. I'll put them down below here. Let's go with a generic x and y on this one. X is going to be speed for faster cyclist. Y is going to be the speed for the slower cyclist. So we have our x and y. So in other words, x is in this direction, the faster one. Y is in this direction, the slower cyclist. And finally, distance equals rate times time can be used, but we use it twice like we mentioned. The question you might have is, well, how much distance did the slower cyclist go? That's the distance from here to here on this curly brace. Distance as a formula is rate times time, so it's going to be distance equals. R stands for the rate of speed, and it's confusing because we have 2 rates of speed. But for the slower one, y is the rate of speed, so it goes here on this part of the diagram. It's multiplied by time. The time is 3 hours, so it's going to be times 3. So I still don't know that distance because we still don't know the rate of speed y. But what we do know is whatever this length is, it's y times 3. Well, that's one end of the diagram. We need to use the formula again on this end of the diagram. But that's the use of the uniform motion formula already once. Any questions, folks, on using that formula? Okay, let's try it again. Here's the other distance. This is the longer distance that the faster cyclist covered in the same amount of time, 3 hours. Distance equals, checking the formula above, it's the rate of speed. And that rate of speed is x. Multiplied by the time, it's the same for both cyclists, 3 hours. So times 3 goes here as well. And, well, we have a diagram, but you know what the diagram provides immediately is an equation. From right here, we can say the 207 kilometer total is just the same as taking this distance first. What is that distance? That's 3 times y plus this distance. That distance is 3 times x. And that total distance from here to here, it could be called 3y plus 3x, or you could just call it 207 kilometers, because we were told that that's the total distance between them. So on the right is the total distance. On the left is the distance that each cyclist actually did. Hey, that's one equation down. If we can get the second equation, we're done considering the word problem. We're just doing algebra from this point. That's kind of the goal with all these problems. Take something complicated like this, do a set of abstraction, and get down to the equations where we're more fluent in solving. Well, that's one equation down. It's a good idea to reread these equations sometimes when you're solving these, because you might have noticed there's one piece of information we still haven't used. It's this part in gray. And good problem solving strategy is that usually a well-written math problem, they're not going to give you information if you don't specifically need it. So that equation is vital as well. It says one cyclist travels 3 kilometers faster than the other. When they say one cyclist, they're talking about x. It's referring to the faster one. It's going 3 kilometers per hour faster than the other. So we can say x equals the 3 kilometers faster per hour is going to be plus 3. Then the other, that one's just going to be y. So the other is cyclist y, the slower one. Hang on, let me double check my color coding. Oh, I have a different kind of color coding. These are both in blue. I used time for green. I think that's why I confused myself. That's y there. When it said one cyclist here, that was x. So it's saying one cyclist, the faster one, is doing 3 kilometers an hour faster than the other one, y, which would be the slower one. That's the second equation. And so now we're in business. This is a system of equations, and we're ready to solve. Let's separate them out. This one has x solved for already, so substitution method looks like it's going to work fantastic. X equals y plus 3 is ready to go. This one's more complicated. 3y plus 3x equals 207. You might not like the numbers, they're large. Let's do a test here. I believe 3 divides 207. There's a little new number trick on that. If you take 2 plus 0 plus 7, you get 9. 3 does divide 9. And so this is kind of sounds like magic. If 3 divides the sum of these digits, you'll divide the whole actual number. 207 divided by 3, it goes in evenly 69 times. So if we don't like the size of the numbers on this equation, that's okay. We could just cut it down to y plus 3. Let me try again. Y plus x equals 69. Next, we can make a substitution. Right here where it says x, we can throw in y plus 3. So we have y plus 3 is 69. And this method is starting to come to its conclusion. It's now 2y plus 3 is 69. Subtract 3 from both sides, and 2y equals 66. So now divide by 2. Y equals 33. kilometers per hour. I don't know if this is like Olympic level or just enthusiast cyclist level of speed. Kilometers per hour kind of confuses me there. But we want to know the rate of speed of each cyclist. And that's one already. The slower one is doing 33 kilometers per hour. That means we're just about done. We take 33 kilometers per hour, this value, and it just goes back up here where y was rather. So x equals 33 in for y plus 3. That means x is now equal to 36 kilometers per hour. So we did it, folks. In my opinion, I would say these are pretty tough problems. So that's why there's 3 of them we're doing on these notes. This is the first one we went through. The best way to get through these kinds of problems are sometimes to draw a diagram, sometimes make a table of information. And this is a problem where a diagram kind of just naturally led to writing down this particular equation right over here. The next problems, we're going to see that maybe a table is a more helpful way to go. But any overall questions on getting through this one? Okay, let's try out this next one then, for example 4. So just another random scenario. We're told a motorboat travels 18 miles downstream in a river in 2 hours. So that's riveting stuff. And this might be exciting if you happen to have a motorboat that you take on the Snake River. Again, be careful with that. It says next, going back upstream, it took 4.5 hours due to the current. So traveled 18 miles downstream, the current is pushing the boat. The rate of speed of the boat and the rate of speed of the water add together. But coming back upstream, same 18 miles, it took 4.5 hours. That's because we're going against the current. The speed of the boat is subtracted by the speed of the current, the water that's fighting its rate of speed. What we want to know is find the rate of speed of the motorboat in still water and the rate of the speed of the current. So this is some interesting information. I don't know how plausible this one is as a word problem, but it's just extra information to practice this formula. An extra example to practice distance equals rate times time. So this is a good one to break down into kind of a 2-column system because there's 2 very different modes of travel. Going downstream first. So let's say here we're going downstream, meaning going with the current. And the next column, we're going to put something for upstream, meaning going against the current. And honestly, for a problem like this one, I don't think this would be a good problem on exam 2, unless I said just specifically, downstream is with the current, upstream is against the current. Because I think that's an easy part of how this problem to just get confused on already with this one. Well, the question said, find the rate of speed of the motorboat in still water, the rate of speed of the current. So let's actually put some variables down next that we have our table here. Let's use the rate of speed of the motorboat for blue. X equals speed of the boat. It's the speed of the boat in still water, but you can be brief when you write out your variable. The rate of speed of the current, let's call this one y. Y equals the speed of the current. Other key information are we have 18 miles going downstream, 18 miles going upstream as well. Let's actually highlight this one. We've spent 2 hours going downstream. That's probably the better one to write. Time is 2 hours here. and 4.5 hours when we're going upstream. So that's a time value here, 4.5 hours. So we're starting to organize the information, and this is what makes the formula kind of difficult. We're using it twice for downstream and upstream. There's 3 variables, but really that means we have 6 different things to account for. Sure, the distances are the same, but we have 2 different rates. We have 2 different times as well, and we have to keep track of all of those things. Let's write down the rates now. So let's do them both like this. No matter what's going on, the speed of the boat should come first. So that's a key part of this problem. And now when it says with the current, that means the speed of the current is helping. These rates of speed are going to add up. And so this is going to be x plus y. When it says against the current right here, the current is hindering our speed of the boat. So that means we have to subtract. It's going to be x minus y on this one. And it's critical that x comes first because y minus x is not the same as x minus y. Let's make that as just a warning on this one. X minus y is not the same as y minus x. This one has the negative associated to y. This one has the negative associated to x. So putting x first on your rates of speed, both of them, is actually a good idea just for the sake of making sure we get this down right each time. So helps with accuracy. The final thing is the boat went 18 miles downstream, distance is 18 miles, and it made a full return trip. It took 4.5 hours, but when it says going back upstream, we mean we're fully returning. So the distance is 18 miles again, going upstream. So I think we've extracted everything we could get out of this. We defined variables. We have distance, rate, time for downstream, distance, rate, time for upstream. Now we can use the formula twice. On the left, distance is rate times time. On the right, distance is rate times time. I don't like that penmanship on the left. Let me fix that. Putting down the formula is a good idea because now we're making 3 substitutions. For distance here, we're going to plug in 18. For rate right here, we're plugging in the x plus y. Let me use the same colors just to match up the color coding. For the time variable, we're told time is 2 hours, so 2 goes right here. There's so many moving parts, it's hard to do color coding on this because there's lots of things you might color code. And so that's distance, the rate of the boat, x plus y, times the time traveled, 2 hours. Then over here, we just do it all over again. Distance is still 18. Rate is subtracted. So this one is x minus y. Time is 2 hours. So times 2 goes here like before. And we've got it, folks. There are 2 equations here and 2 unknowns. We've taken this entire math problem, just a couple sentences, a few sentences of text, and look at the algebra that it implies. There's a lot of stuff. But once we're down to the 2 equations, it's not so bad from here on out. Both of the equations simplify. We can divide by 2 in each one of them. Let's do that here. Divide by 2 on this one. We have x plus y equals 9. Divide by 2 here. We have x minus y equals 9. We can next solve this system of equations by elimination. Let's stack them. X plus y equals 9. X minus y equals 9. When we add them together, we'll get 2x equals 9 plus 9 here for an 18. So then divide by 2, and x equals 9 miles per hour. And that one was the speed of the boat. Once we know x is 9 miles per hour, we can come and grab, say, maybe this equation again. X plus y equals 9. Put 9 miles per hour in this spot. So 9 plus y, or hang on, let me take another look at that. Oh, I think I made a mistake on this. Let's do a little bit of surgery here. Sorry for that mistake right at this spot right here. I mean, I guess that's the danger for doing these kind of problems. There's so much stuff to substitute in. Making one substitution mistake is going to cause weird things to happen. I put in from time here 2, but the actual time is 4.5 hours. So let's make this correction right here. 4.5 is what's going to multiply in this spot. Let me put an extra parenthesis around it. That means when we go to divide by this, 18 divided by 4.5 is going to give us 4 altogether. So 4 equals x minus y, or x minus y equals 4. Over here, when we divide by 2, it was x plus y equals 9. So sorry for the backtrack on that one. I've copied down here, x plus y is 9. Let's take this one, copy it below. X minus y equals 9. Excuse me, I'm using my same result from before. X minus y equals 4. That's the revised number. Now when we add this together, we get 2x equals 13. This is looking a little bit more reasonable. Divide by 2, and x equals 6.5 miles per hour. Okay, that's working out a little bit better. Now we'll take this one right here. X plus y equals 9. And I knew I had a mistake once I got to this level, because when we said x is 9 miles per hour, we were going to put 9 right here, and then that would mean y is 0 miles per hour. That would not make sense with the information given. Y has to have a positive rate of speed of the current. So let's put in the correct value now, 6.5 plus y equals 9. We can subtract 6.5 from both sides and get y equals 2.5 miles per hour on this one. Then at this stage, we did it, folks. The speed of the boat, let's zoom in to see the rest of our work here, is x, and it was going 6.5 miles per hour. The speed of the current is y, and we're told that this was going 2.5 miles per hour. That's why this person covered 18 miles in just 2 hours, but covered the same 18 miles in 4.5 hours. It's because the rate of the speed here was just, let's see here, 4 miles per hour. Rate of speed here was 9 miles per hour. But we did it, folks. Once we got to the x and the y value, this problem was right at its end. Any questions on getting through this one? Okay, we have one last problem to go on these notes. And this seems to be a pattern in the class so far for some reason. We always seem to get to the very last problem in the notes and then essentially run out of time. We have about 6 minutes, but this is not a 6-minute problem. This is like a 12 or 15-minute problem, really. And I would hate to start this problem just to come back to it halfway or a third of the way after a long weekend, an exam, and then coming back to this again. It feels like we'd have to restart it anyways. So this will be a good stopping point for us today in this class. Any last questions about any of the problems here so far before we call it a night? Okay, well, have a great night, folks. If you have any questions about scheduling your exam, don't hesitate to write. I'm going to be sending out to just another reminder with the same instructions from before, just in case that email got lost or that message on Canvas got lost. So check your ISU email or check your Canvas messages in the morning, and it'll have that link if you still need to schedule that exam. But otherwise, have a great night, folks, and I'll see you all next week.